Tell whether the number is written in scientific notation. Explain. Before we talk about this number here in Part A, let's look at a few examples of numbers that are written in scientific notation. For a number to be written in scientific notation, it should consist of a factor times a power of 10. So here's a few examples. The factor is 1 2/10, and the power of 10 is 10 to the third power. Another one, 1 times 10 to the 8th power. 2 237 thousandths times 10 to the negative 11th power. 9 9/10 times 10 to the 50th power. These numbers all consist of a factor times the power of 10, and they're all written in scientific notation. But not every number written as a factor times the power of 10 will be in scientific notation. There's two more conditions that they have to meet. First, the factor needs to be at least 1 and less than 10, and notice all these factors are at least 1 and less than 10. And then the power of 10 needs to have an integer exponent, and notice each of these has an integer exponent. So these are all examples of numbers written in scientific notation. Now let's look back at the number we have in Part A. We have a factor times a power of 10, so is this written in scientific notation? Well, first we can say the factor 2 5/10 is at least 1 and less than 10, so it passes that test. We can also say that the power of 10 has an integer exponent, -9, so it also passes that test. So the number is written in scientific notation. Part B. Tell whether this number is written in scientific notation. First of all, we have a factor times a power of 10, so that's true. So let's look at the factor. Well, notice that the factor is not at least 1. So this number doesn't pass our test. So the number is not written in scientific notation. Tell whether write the number 2 75 hundredths times 10 to the negative third power in standard form. We're given a number in scientific notation, and we're asked to write it in standard form. Let's start by writing the number. To write a number in scientific notation in standard form, write the first factor and use the exponent to determine where to move the decimal point of the factor. So let's write this factor, and now look at the exponent. The exponent tells you how many places to move the decimal point and which direction. Because the number here is 3, we move the decimal point 3 places, and because it's negative, we move to the left. If it were positive, we would move to the right. So move 3 places to the left. Let's show the path. So the decimal point moves from here to here. Now notice that we have places without digits, so we need to write zeros as placeholders. Write a 0 here, and another here. And notice that our number is going to be a decimal number that's less than 1, so we need a leading 0, don't we? So here's our number. We don't need this path anymore, so let's erase that. And for this number given in scientific notation, the standard form is the decimal number 275 hundred thousandths. Let's take a look at another problem. Write the number 6 3800 times 10 to the 7th power in standard form. So here we have another number in scientific notation that we want to write in standard form. Let's start by writing the number. Now try getting started writing this in standard form yourself. What you do is write the first factor and use the exponent to determine where to move the decimal point. The exponent is positive, so move the decimal point 7 places to the right. Let's show the path. So here's where the decimal point will end up if we move it 7 places to the right. And notice that we have places without digits, so let's write zeros as placeholders. And with the zeros there, you can see that when we move the decimal point over to here, what we actually have is a whole number, so we don't even need the decimal point. So let's just erase it over here, and we can erase our path. And to complete our standard form, we should write commas starting from the right every 3 places. 1, 2, 3. 1, 2, 3. So in standard form, our number is the whole number, 63,800,000. Right? An object with lesser density than water will float. An object with a greater density than water will sink. Use each given density in kilograms per cubic meter to explain what happens when you place an ear of corn in water. So what's this problem about? Basically, it's about comparing the density of a solid object with the density of water to see whether or not the solid object will float. What is density? It's a measure of kilograms per cubic meter. And what does that mean? Well, kilograms is mass, which is just like weight. So it's like the mass or weight per cubic meter for the same amount of volume. So which density means which object or which thing, water or corn, has more weight per cubic meter. So imagine a cubic meter of water and a cubic meter of corn. This number gives the weight of the cubic meter of water, and this number gives the weight of the cubic meter of corn. If the weight of the corn is greater, it will sink in water. And if the weight of the corn is less, then it will float in water. So, to explain what happens when you place an ear of corn in water, what we need to do is compare these numbers. Let's write each number in standard form. For 1 0/10 times 10 to the third, write the factor 1 0/10, and I'm not even going to place the decimal point. I'm going to imagine where it is. It should be right there between the 1 and 0. We want to move it 3 places to the right. Well, to do that, we need a few zeros. So write in 2 zeros. And then when we move that decimal place 3 places to the right, 1, 2, 3. This is where the decimal point would go. We don't need it there because that makes 1,000 a whole number, so we don't need the decimal point. So the density of water is 1,000 kilograms per cubic meter. Now let's check it out for an ear of corn. For 7 2100 times 10 to the second power, write the factor 7 2100 But again, I'm not going to write the decimal point, I'm going to imagine it here. And we want to move the decimal point 2 places to the right. We don't need any zeros this time because we have 2 digits. So we go here and then here on this side of the 1. And we don't need to write the decimal point because we have a whole number, 721. So the density of corn is 721 kilograms per cubic meter. Now we can compare the density of the solid object to the density of water and use the rules we're given up here to decide what the corn will do in water. And to answer the question, we can say, because 721 is less than 1,000, an ear of corn is less dense than water, so it floats in water. So, if you know the density of a solid object, you can compare it to the density of water, and that'll help you decide whether or not the object would float or sink in water. A dog has 50 female fleas. How many milliliters of blood do the fleas consume per day? Well, this can't be much fun for the dog, but let's take a look at this problem. The dog has 50 female fleas. We want to know how many milliliters of blood the fleas consume in a day. And take a look at this photo caption. It tells us a female flea consumes about 1 4/10 times 10 to the negative 5th power liter of blood per day. So this number in scientific notation represents the liters of blood consumed by one flea. We can multiply it by 50 to find how much blood is consumed by all 50 fleas. So here's an expression for the number of liters of blood consumed by 50 fleas in a day. To evaluate the expression, we can start by taking the first number in scientific notation and writing it in standard form. Start by writing the first factor, and move the decimal point 5 places to the left and write zeros as placeholders. And don't forget to multiply by 50. So now we need to multiply. Let's come over here at the right and do the multiplication. Start by multiplying by 0, and you'll get 0. Now 5 times 4 is 20. Write the 0 and carry the 2. 5 times 1 is 5, plus 2 is 7. And then we have 5 times 5 zeros. To place the decimal point in our answer, we need to count the number of decimal places to the right of the decimal point. 1, 2, 3, 4, 5, 6. So we need 6 decimal places in the answer. So the answer is 7 ten-thousandths. But this is the number of liters consumed by all 50 female fleas. We want the number of milliliters. There's 1,000 milliliters in a liter, so we need to multiply this number by 1,000. And when we do that, we'll find that it's 7/10 milliliters. So to write an answer to the problem, we can say that the fleas consume about 7 ten-thousandths of a liter or 7/10 of a milliliter of blood per day.